Terus, follow up from Dark Matter Awareness Week last year. It was an event in a week where a lot of institute gave talks, almost the same talk. They have their own standard talk, they have notes, they have other materials, videos. Right? It's a activity to promote, to tell people that this is an important subject. Right? You can see all over the world, including Malaysia as well. Right? So you can see there will be some slides for the rest of the speakers. They might use the standard slides from here. Okay. But my emphasis will be on building the first Malaysian radio telescope with the motivation of studying dark matter. So I will move towards that, and the rest of the talk about the history of dark matter, the experimental searches, the theory, the radio frequency interference, all that will be given by the other speakers. Right, so my talk will be quite general. So in short, radio astronomy is a very important part of multi-wavelength astronomy. Right, to comprehensively observe objects from the sky, we have to observe in all the frequencies. Different frequencies show different features in celestial objects. The famous one is optical, but this famous picture of Milky Way, you can see dust covering the background source, and we can use radio astronomy to look beyond the dust. And I picked the two up because only optical and optical wave and radio wave can reach the ground. For the rest of that, you have to go into space, because all the other wavelength has been will be absorbed or reflected by the atmosphere. Right, so that's why radio astronomy is important, and anyone can do that with do the observation with the right instrument. Right, so in Insti Melaya, just a short timeline. Started in 2005, observing basic detecting radio bursts from Jupiter, and then we move on to do observation of meteor, the radio wave, and then we found out that radio astronomy observation has similar to your light pollution. For optical astronomy, we also have our own pollution, which is the interference, radio frequency interference. So we started this study, and this will be there will be a talk by Encik Ruslan on this after the break, in order for us to establish a radio quiet zone, hopefully in the future, anywhere in Malaysia where we have the lowest RFI. And then with some grants, we managed to build some radio telescopes, and we have a solar radio telescope and a fully robotic radio telescope, the left hand side. And then we found out that we have built this on a very high RFI area, so we move it to a different area in Institute Tanah dan Ukur Negara in Perak, low RFI. And then we started our solar radio monitoring, as well as some test observation of galaxy clusters, in order for us to learn about dark matter. And we also have collaboration with University of Manchester. So these are their telescopes. They are big telescopes, but we use the small telescopes, and move on to the future. Hopefully we can be part of international arrays of telescopes, which is called interferometers. A little bit on the dark matter, right? Actually, I shouldn't be going deep into this, because this will steal some thunder from the rest of the speakers. Just a little bit, these days cosmology is called precision cosmology. We want to be precise with every values that we have, and it is generally accepted that the best model to describe all the matter in the universe is lambda CDM, cosmological constant, cold dark matter, obtained from data from the Big Bang model theory, from the cosmic microwave background satellite data. It says that only 4% of the atoms, 4% of the matter in the universe is matter that we know, ordinary matter. So the rest we don't know. 23% is dark matter. It's accepted as cold dark matter now. Again, this will be talked about later. And the rest is dark energy, 73%, which in theory, in short, the energy that accelerates the universe. So this I call dark sector, right? Dark energy and dark matter. A little bit on dark matter. The basic idea comes from looking at dynamics of stars in galaxy, right? The mystery of stars near the edge of the galaxy moving not as it's supposed to be, right? In short, right? So, again, who will talk about that? Nosia, I think, will talk about that. It's not just in radio astronomy. Dark matter has been studied a lot in optical as well through gravitational lensing, Einstein ring, if you heard of that. Boleh tengok if you have heard of gravitational lensing, Einstein ring, and also X-ray astronomy as well, high energy astronomy, looking at hot cloud in front of background source. This effect is called the Sunyaev-Zel'dovich effect, Z effect. But now we can observe dark matter indirectly through what we call neutral hydrogen H1, which is actually emission emitted from neutral hydrogen changing its energy state, right, naturally. So if we can observe neutral hydrogen, we can observe hydrogen. Hydrogen is the essence of matter, right? So we are detecting matter, right? And the next testing ground, our project here is looking at not just galaxies but clusters of galaxies, right? Because clusters of galaxies have their own gravitational boundary. They are called virialized objects. The other one is collapsing objects. So, but we focus on virialized objects. So we focus on this. Alright, so this is to show you that radio signals, what we get is spectrum, and then we deduce from the width of the spectral line, and then we can compute the velocity and hence the mass of it. So in short, I say it's more complicated than that. There's a lot of errors as well, instrumental errors, we have to look at that, foregrounds. Right, so this is to put it in a simple word. This slide is to show that we are looking at low redshift galaxy clusters only. We don't need to look at high redshift galaxy clusters because that will show you information of the early universe. Right? We don't need that. We can do that actually because that will show you primordial dark matter. But what we want to do is low redshift galaxy clusters. I'm sure you know about redshift, Doppler shift, right? Low redshift means it's closer to us, it's moving a bit slower when compared to us, compared to the high redshifts. And also the signals are not that low, not as low as the cosmic microwave background, right? Cosmic microwave background is the signal furthest away from us to show us the origin of the beginning of time, the Big Bang. So it's not as sensitive as that, so we can use a low resolution, low precision telescope. But the problem is not the collecting area, but the temperature sensitivity. We have to observe over a long period of time to get a comparable detection. Again, that's in short. It's not as easy as that. But it's doable. It's within the range. Some tests has been done with a few able catalog clusters, 400, 539. Their peaks are 70 millijensky per theory. It has to go above 10 millijensky over 3 days. So it's doable. So because of that, we did an MOU with the Jodrell Bank Observatory in England to use their 7-meter telescope to do further testing. So I'll show you some results. Initial tests. We did we selected few candidates. So the first candidate's well outside its bandwidth, so no. So the second candidate is at the edge of the bandwidth. A lot of interference as well, so no. But only the third one, we managed to get some signal free of interference and within the bandwidth. So I'll show you the early results. Right, not much you can see here. This is over integration time of an hour. Right. So a lot of interference, but I can get rid of this interference, no problem, from the software. But I just want to show you that the detection should be somewhere around here, and the idea is to do observation over a long period of time, month probably. So that's the problem. Maybe you can ask. Maybe you have this question of why don't we use this? We use telescopes that we have all over the world. Why don't we use the telescopes to do this? The problem is they won't allow us. Right? They won't allow us because we need to do this over a month. Right? 4 or 5 months to get good detection. So no telescope will allow us to use 4 or 5 months. Right? The most is only about a week or so. They have their own priorities. Right? So that's the motivation of building our own telescope here. Right. And of course there is more to that. There's just an early test. So the future of this particular project is we already established collaboration with the New Zealanders, Auckland University of Technology. We will use our results. If it's successful, test it on the 12-meter telescope. The reason is they're not using it at the time being. Right? They have few telescopes, but they're not using this one. So they say they might can fit some schedule into the schedule for us to use this. So the future of the group, in short, we want to go international, right? Everyone else. So we have the platform of Southeast Asia Astronomy Network. Right? We have so it's not only Malaysia have radio telescopes, radio astronomers. Thailand have a few. Indonesia as well. Indonesia have few telescopes. Thailand have one 12-meter telescope donated by a radio telecommunication company, but they haven't converted it for radio astronomy purposes. But the three of us can form an array network, right? So that's the plan, right? And all three have agreed. So it's a matter of synchronizing. And one of the advisors of this network is Professor Michael Kramer, who is also one of the directors of an international project which is called Square Kilometer Array. So they want us to join them to be a research hub for them. So if we can gather enough people, enough researchers, we can have our own center and provide expertise for them. So we will be part of them. So this is the pinnacle, the top of radio astronomy experiments, this will be more sensitive than any satellite surveys, right? There we have a lot of antenna telescopes over 1,000 kilometer radius. There are different type of arrays as well, looking at different frequencies. So they will be the top. So we want to join that, right? So the task now is to gather enough people, right? We don't want to join them with only like 4 people. Okay. The group, I'd like to introduce the group. That's me on top, and one of the co-founder as well, Prof. Zaino. Alright, he's not here. I can't make it. And we also have a PhD student, also a lecturer from Masasi. Norcia, she will talk about theory of dark matter, especially rotation curve of galaxies, not clusters of galaxies, but galaxies. But Angkasa Salwa will talk about clusters of galaxies, and also searches, experimental searches of dark matter, right? And then Saiful will talk about, actually he's the first after this, will talk about the history of dark matter, right? How it involved, the idea, and the people involved in the history of dark matter study. We have research assistant Zul Fazli, part of the group as well, and also assistant science officer Muhammad Khairi. So that's our group. Dark matter, our radio cosmology group consists of a few more, including Roslan, who will talk about radio frequency interference, as well as Zeti will talk about radio solar monitoring. So that's our website. You can look at that, or you can go Google search for Radio Cosmology UM if you need research. As usual, thanks to my department for their support in Istimlaya, especially for their grants. Jordan Bank Observatory in UK, a lot of help from them, advice as well, and the International School for Advanced Studies in Italy. They are the one who started the Dark Matter Awareness Week, right? Professor Paolo Salucci in Trieste, Italy. Agensi Angkasa, of course, for their help promoting our work as well. Institute Tanah dan Buku Negara for letting us move our telescope there with the low RFI area. Institute of Science Biology UM as well, because they are giving us a piece of land there. It's in the farmland, call it. So we can build one telescope there. So they're letting us. So thanks to them. And also grants. I have a few grants there. 2006 is the latest, so mostly the first to give me money. Alright, so that's our lab. Radio lab, simple lab, the testing lab. You can see students hardworking there. This is in Instone, in Perak. The telescope, the software, the sky map in the software. You can see there's a observation of the sun, example, and some Jupiter instruments, and radio frequency interference. And that's a spectrum analyzer for RFI measurement. Yep, so any questions now, or you can ask later as well?